Good morning everyone. Welcome to Wireless Future. My name is Erik Larsson and I'm here today with Emil Björnsson. We are both profs at Linköping University in Sweden, and Emil is also a prof at the KTH Royal Institute of Technology in Stockholm, Sweden. Good morning, Emil. How are you today?
I'm fine. How are you?
I'm good, thank you. Great to have you here, and I'm delighted to have the opportunity to speak with you today. And the topic that I'd like to talk about is, of course, Massive MIMO. And specifically, where do we stand? Where does the technology stand? And where is it heading? So, as a piece of background here, we've both been in this race for about a decade now. And at least for me personally, when I started to work on Massive MIMO back in 2009, I obviously believed in the technology. I was a hardcore believer from the very outset, but I never believed and imagined that things would happen so fast and that Massive MIMO would become a commercial reality so fast. And the other day I went to Google and I typed in Massive MIMO products, and I was baffled. The first hit that I got was from a firm, I think their name was Global Data, and they showed bar charts over how many products that the different vendors had right now on the market on Massive MIMO. And I think the leader there was CTE. They had like 25 products that were branded as 64T, 64R. As I understand, that means 64 transmit, 64 receive. And Huawei had a similar number. Ericsson had slightly fewer, and there were a couple of other vendors as well. And I was also heavily surprised to see that there were products that were branded as Massive MIMO and they were sold under the label 16T by 16R. So, Emil, what's really going on here? What is it that we are seeing? What does this mean to start with? 16T by 16R, is that really Massive MIMO?
Yeah, so there is a lot of Massive MIMO products out there, and I think one of the reasons is that there is different form factors that people are interested in different countries, different types of deployments, and also there's all the different frequency bands that are being used now in 4G and 5G that these different products can be used for. And that also tells us why we need many different products to different markets, for example. And I think to really say something about what this product really contains, it's important to start from how we are building base stations traditionally. So traditionally, a base station consists of three different parts. So you have the antenna that is radiating the signal in a fixed way. Then we have the radio that is generating the signal that the antenna should be transmitting. And then we have the baseband unit that is determining what signal to generate. And traditionally, we have had the antenna in the top of the base station, and then the radio first in the basement next to the baseband unit. And then with time, the radio has been so small that we can put it up in the tower together with the antenna. And then what this Massive MIMO product is some kind of integrated antenna and radio, where you take the antenna and the radio and put it together into one device. And since things have been so small now, we can put multiple of them in the same device. Because if you would try to build MIMO in the past, we will have to have so many different boxes, so many different cables, which is the reason sort of why we have been talking about MIMO products for decades now, but it's first now that Massive MIMO really is starting off. So I would say that what these different boxes, 16, 32 and 64 boxes are containing is a number of different radiating elements or antenna elements, which are then connected to radios. And then there's the cable still to the baseband unit. And within one of these antenna panels, we could have maybe 64 or 128 antenna elements. And then what is varying between these different products is the number of radios. So we have 16, we have 32, or we have 64. And then they like to point out that we have equal number for the transmission and the reception, because that's not usually or always the case in real products. For example, an LTE phone might only have 2 receive antennas, but 1 transmit antenna.
Right. So, hey, I find this immensely confusing, as an academic, right? When I see like 64T, 64R, I think of a 64 by 64 matrix valued equation. And now you're saying here that well, 64R and 64T might not be what it seems to be. Are you suggesting that the 64T, 64R arrays don't have 64 baseband chains, or did I not get that right?
No, so that is really the number of baseband chains that we're having.
Yeah.
And then as an academic, I have for a long time used the term antenna to describe the number of baseband chains that you're having, the dimension of these matrices that we are dealing with in the academia when we are computing what kind of algorithm to utilize. But then there could be this different number when it comes to the number of actual radiating elements or antenna elements, if we like to call them like that. So it might be that the number of antenna elements in a 64 product and in a 16 product could be the same. It's just that the number of transceiver chains that we have put into this product is different. And that could be depending on what kind of deployment scenario that these different operators that are going to buy the product have in mind. Because the arrays of elements here, in order to fit them into a small box, usually they are put in some kind of rectangular shape. So you might have 4 different rows, and then you might have 8 antenna elements next to each other, and each of them have 2 polarizations, so they're essentially 2 antenna elements. In that way you can build up 64 elements, for example. And in some of these ones you even have 128 elements. So you have 8 by 8 times 2 polarizations. And then when you are building the product, you can decide on how many transceiver chains you would like to connect these ones to. And that is determining the number that we have, 16, 32, and 64.
Right, I see. So, but so is my understanding correct then that if you buy one of these boxes, right, with a 64T64R label, could you do like special multiplexing, full blown with 64 terminals at the same time, or is there something else going on here?
That could also depend a little bit on what kind of implementation that are going on there, because in this box you have these 64 transceiver chains, so you can sort of get 64 dimensions out of them. Then depending on the implementation, you have a digital cable that is sort of providing you with the baseband data and send it to the baseband unit, and that cable might have a limited capacity as well. So it might be that you have your 64 dimension, but the cables are meant for just supporting maybe 32 or 16 dimensions, so some elementary compression is going on inside the box, and then you send those signals to the baseband unit. So it might be that you have different dimensions at different places. So you sort of start with having a lot of antenna elements, maybe 128, then you have 64 transceiver chains, and then what you send off to the baseband unit might be a smaller number still. So there's a lot of confusion when it comes to what kind of dimensionalities you have at different places in the same system.
Right. Wow. Yeah. So, this commercial world of products seems so complicated. I guess I'd rather stay in academia. So could you illuminate a bit? Another thing I don't think I've understood well here is, I do understand that there's this range of products, right? And you can buy boxes in different shapes and colors and with different cables and different antenna ports and elements and so forth. But which frequency bands are these products really for?
So when it comes to these early 5G deployments, there is 2 main bands, I would say, that are being used right now, and that is the 3.5 gigahertz band, also known as the C band, and the 2.5 gigahertz band. And I think the main band that the most number of operators have bought licenses for is the 3.5 gigahertz band. This is where these Massive MIMO radios are particularly being used now.
Right. So I understand, these products are for the sub-6 gigahertz market, right? 2.5, you mentioned 3.4, was that what you said?
Yeah, for 3.5, usually you call those numbers, but then it might be that the actual frequency range is somewhere there, it's a ballpark number.
Right, sure, yeah. Obviously those are the most valuable frequencies, as we know, right? So is this TDD or FDD?
So as far as I've understood, these bands are TDD in all the countries where things have been deployed. So some of the main markets now where you can buy 5G phones and use them is the US, South Korea, and China. And in those countries, I have understood that these are TDD spectrum, and it might be between 40 and 100 megahertz in those bands that are being utilized.
Right, right. So where is Massive MIMO mostly being deployed now? I mean, which are the main markets for these products?
So one of the complications when you try to find a good answer to this is that you can find numbers on how many base stations with 5G that have been deployed. But as you mentioned, you have the 16, you have the 32, you have the 64, and then it might also be that some operators are deploying 5G in other bands, like 700 or 900 megahertz band, for example, and then it's probably not Massive MIMO products that they have put up there so far.
Right.
But I know that Sprint Mobile, which is now T-Mobile in the US, they said last year that they're going to put up 1,000 sites with Massive MIMO, and that they are now deploying 5G sites, 1,000 per month, starting from May, June this year. And in China,
so in the United States,
in the United States,
number,
so they are selecting major cities, and then they are turning on things city by city there.
Right. And how about the rest of the world? I mean, you mentioned China.
Yeah, in China, I read that there's supposedly 400,000 sites with 5G, and that should grow to 600,000 sites with 5G during this year. And what fraction of that is using this type of Massive MIMO products is very hard to know. I don't have any numbers on that, but even if it's a small fraction, it's still a huge number of products. And I've heard on the Mobile World Congress as well that it is a large fraction of the base station that are being sold now that are using these Massive MIMO products.
Right. But I mean, do you have any feeling, is the deployment, I suppose the deployment is still in its infancy, right? I mean, if I drop a pin at random on the globe here, what is the probability that I'll be covered by a Massive MIMO base station? Do you have a feeling for that?
That probability is incredibly small, I would say, because in many countries, including Sweden where we are, there is some networks, but it's not like many users are using them so far. And even if some operators just a few months ago started to say that now we are turning on 5G, it's not like anyone is using it really in this country. So I think there's a lot of countries where there are trials and where operators try to deploy 5G, but the number of countries where you have a commercial network, that is much smaller.
Right. I suppose the terminals also have to support the 5G, right? I mean, support the Massive MIMO operation. Is that so?
Yeah, definitely. That is so. And I think last year there were a number of phones that were released with 5G support. But then you also come down to, okay, there are different bands in different countries. Does the 5G phone support all of those bands or not? And I think this year people are waiting for the iPhone, which should come out in a month or so. And then the question is whether that one will support 5G and which bands, for example, that will be. I think people are still waiting. It's still just some few flagship mobile phones from some companies that are supporting 5G in certain bands.
Right, so the Massive MIMO enabled iPhone, yeah. So would, I mean, you mentioned here that most of this is TDD, right? So is anyone doing FDD? I mean, are any of these products for the FDD spectrum?
So I know that there have been trials with the branded Massive MIMO in a number of countries, and there are FDD bands being used in 5G, but whether there are actual Massive MIMO branded products for that, I don't know so far.
Yeah, right.
But it seemed like that nowadays all the different countries, whether operators talking about 5G, they're really saying that TDD is the future. That is where we would like to use our networks, which is a bit funny because I think maybe 5 years ago when we were working in various research projects around Massive MIMO, there were always this talk about that FDD is the simplest thing to utilize. That is where we have spectrum, but it's also the thing that is easiest to deal with, because if you have TDD spectrum, then you need to coordinate things with the operator that has the next spectrum. So TDD really means that you are switching in time between transmitting down to the user and up to the base station. And if two operators have bands that are next to each other, well, then they will have to do this in a synchronous manner. And I remember some operator telling us that in China you can do this because you can have strict regulations. In Europe you can't do this because it's no one really would like to have these strict regulations on how they run the networks. But now when people have realized that Massive MIMO and TDD is the very good combination, then it seems like people are not so afraid about these type of things anymore. They see the benefits.
Right, right. I mean, yeah, that's great to know. I mean, so are you saying that the TDD, FDD debate is dead now? I mean, it used to be a fierce discussion, right? And I mean, both you and me have been heavy advocates for TDD and reciprocity beamforming for many years. Is that debate settled now? Is that what you are suggesting, Emil?
I'm not sure how many people had actually been saying that FDD spectrum, where you have two different bands, one for uplink and one for downlink, where you don't need to deal with this type of synchronization issues, that this is actually the best option. I think there is a lot of researchers that have been saying that, well, if an operator already has an FDD band, it's very cumbersome to change that to TDD, because that means that all of the neighboring bands will also have to change. So it's a large regulatory thing. It won't happen. And for that reason, we would like to develop research methods or algorithms for Massive MIMO that also can work in these bands. So it's sort of a practical approach to it. And then they might in the research paper say that, look, it works equally good as the TDD. But if you talk to them at a conference, they say, no, of course, TDD is what you would like to do. But if you're forced to do FDD, these are the methods to utilize.
Right, yeah. But well, while of course, as we know, TDD is fundamentally better, right? Okay, so now when you say TDD here, and we speak about these products, do we know for a fact that what really goes inside of the box is true reciprocity-based multi-user MIMO beamforming, or is there something else that we know that?
Yes, so in the 5G standard, there are 3 different modes of how to learn the communication channels. You know how to point the beams with these adaptive arrays, which can sort of send beams in different directions, focus to the users, and that way you can serve multiple users at the same time. And that is really the core benefits here. And you're supporting these different modes, and then 2 of them are based on that you are not utilizing that you are sending in this over the same channel, both in the uplink and the downlink, but you are instead just learning the channel in one direction, quantize the information and send it back. And this is what we have really been pointing out, that this is a huge weakness, because the more antenna elements you're using, the more RF chains you're using, the more complicated it will be to implement this and get the right granularity in your beamforming as you would like to have. And that is why this reciprocity-based beamforming is what everyone at academia is pointing out is the thing to utilize. Then what have been actually implemented in this product is much harder to know, because the standard is supporting multiple things, and then it's always up to the vendor to decide on what they're implementing. And I've been talking with different vendors, and several of them have been confirming that they have products that are capable of doing this type of reciprocity-based beamforming that we are pointing out that this is what you would like to do from a theoretical perspective. And that it also has been complicated to implement this, because you never want to start from a blank sheet of paper when you're doing implementation. You build it upon previous works in your product line, and that it has been difficult to get the right type of possibility of switching between uplink and downlink and keep all of the synchronization so that you can learn the channel in one direction and utilize it in the other direction. But I've been told that several vendors are supporting this, and they are using this type of interference rejection methods like regularized zero forcing and things like that when they are supporting the feature. Then whether all the products are using this all the time, I'm not so sure about that is actually going on. For example, you have this issue that the base station is typically transmitted with 100 times more power than the mobile phone. So if the user is far out in the cell and have a bad channel, then they might have found it difficult in their implementation to learn the channels from a signal sent from the weak user. and then beamform back. And then they might be switching with other things that give them a bit more security because they will like to build things for the worst case setup. And you also have this, there's also this additional thing which is more from a practical perspective, that since these 2.5 and 3.5 bands are having worse propagation conditions than the, say, 700 or 900 megahertz bands, where the same vendor or same operator might have also a base station co-located, they might be building a 5G network where you do the uplink in a lower band and the downlink in these Massive MIMO supported bands. And that also makes it difficult in practice to utilize these methods that are theoretically the best ones.
Yeah. Right. So what you're saying is that, I mean, if you have the uplink on one band and the downlink on a different band, then you can't directly utilize reciprocity, right? So you have to fall back on this FTD style estimate and feedback the channel solutions. Yeah, that's interesting.
Yeah, so this is really a way of being able to tell the user that you have 5G everywhere, because we are putting the uplink in a previous 4G band and then we put the downlink in the 5G band, and in that way we can claim that we have better coverage with 5G, even if you can't use these methods everywhere.
Right. Yeah, so this issue with coverage, I think that's something we'll have to come back to at a different occasion, because there are like a lot of technical difficulties here, right? I mean, one thing I think you mentioned is the imbalance in power, the fact that the base station typically has like 100 times more power to spend on the downlink than what the terminal has in the uplink. But so one thing I was eager here to understand in more detail is, now if we look at Massive MIMO technology, there are obviously endless with academic papers, and there are textbooks, right? I mean, we both have a textbook. And when you look in these papers and books, you'll see different, of course, sorts of analysis. And you'll also see numerical charts with performance, claims on spectral efficiency, on coverage, on uniformity in the quality of service, and so forth. So now looking at these products and actual commercial deployments and field trials that we're aware of, how do the numbers in practice compare to the predictions in the academic papers? Could you shed some light on that?
So I think there are two different ways that one can look at that. One of them is that if you are comparing a Massive MIMO base station, I would say 64T, 64R, with a previous base station, say 80R, that was not called Massive MIMO, is the improvement in performance aligned with what theory tells us. And that seems to be the case. I was listening to a talk by the CTO at Sprint last year, which is now T-Mobile in the US, and then they were pointing out that when they turned on in their commercial networks, Massive MIMO, they saw this type of gains of, say, 4 to 20 times data rate improvements. So going with having 8 times more antennas or 8 times more RF or transceiver chains should give you in the ballpark a number of 8 times gains. So that seems to be consistent with what they were getting, and they saw in particularly good gains in the uplink, because the uplink was not as advanced in 4G networks in the past. Then when it comes to sort of comparing things with what we have seen in theory, well, in a way you can see similar types of performance. Now, there have been a progression when it comes to field trials in real network, but still when they are putting up a base station and they are experimenting with it just to verify that it works out. And the latest thing I saw was that T-Mobile and Ericsson had a deployment in the US in the 2.5 band using 100 megahertz, and they achieved 5.6 gigabits per second. And to do that, they were serving 8 different users. To each user, they were sending 2 so-called layers or data streams. So you're sending 2 streams at the same time over different polarizations to the users. And then they were achieving, say, 700 megabit per second per user here. And if you break down those numbers in terms of so-called spectral efficiency, in the cell you have 56 megabits per second per hertz. 56 bit per second per hertz, and that is sort of a number that you can see on many curves in the Massive MIMO area, and it's something that you can see practical. I think if you implement the system, you use 16 QAM modulation, then you multiply the number of users, use a channel code, and so this seems to be a reasonable number, which is in line with what we have been showing in graphs in the academia. Then there is all of these trials that people have been doing more from an academic perspective. There is the Bristol World Record in Spectral Efficiency from 2016. I think they had almost 150 bits per second per hertz, which is still, say, 3 times as much. But it was also sort of a very controlled environment where you were having huge modulation formats like 256 QAM, I think.
Right, so the 150 bits per second in hertz, but that was in the lab, right? From the Bristol folks. But you said
that was in the lab, and 22 users, 128 transceiver chains. Right. So it was still far off from what was considered in the real networks. Right.
But earlier you said like 56 bits per second in hertz, and that was in a real deployment, right?
That was in a real deployment. Then you can never know what they were doing in terms of how they were selecting where the users are going to stand, for example. But since they were using 16 QAM modulation, I would guess from the spectral efficiency number per user and a reasonable type of modulation format encoding, then I think this is something that you can actually gain in a real network if the users, all of them, happen to be in the center of the cell.
Right. So, but do we know anything? I mean, was there like interference? Were there multiple cells or multiple sites? Because once we have multiple sites, they tend to create mutual interference, right? And was there mobility? Because mobility is a huge challenge in Massive MIMO, right? Where you need to re-estimate the channel responses every time that your terminals move just half a wavelength. You need to redo the whole thing. Do we know that from these numbers?
No, we don't know that. Yeah. I would guess that it was a rather controlled experiment. But these press releases are often not providing all the details as we as academics would like to get.
Yeah.
And sometimes the press release is also clear that it's been written by people who are not in the engineering part, because they might be making weird claims, such as that 64T, 64R, as we talked about before, they add up those numbers and say that we have 128 antennas. So even if it's the same type of connection, it's just the switch between them for uplink and downlink. Right. So sometimes there are these weird statements in this press release as well. But I think the numbers as such are real, and we could speculate on how they were achieved in the way that we just have done.
Right. But I mean, how do we even know that we can trust these numbers, right? I mean, it's like if you go to the car dealer, right, and then it states the new car states that it can do like 40 miles per gallon gas efficiently, and when you actually drive it, you only get 30, right? So do we know that with the Massive MIMO products and with all the numbers that are coded from commercial deployments, and perhaps the academic field trials are like more open and offer more openness, but do we have a feeling for that?
I think that if you look in the press release, they might sometimes say in the sentence or so that this was the peak number that they were measuring, and then you don't know what they were measuring more on the average.
Right.
And this is also the interesting thing in general when it comes to development of wireless standards. There have been such a big focus on getting the peak rate up to a huge number, but nowadays it's more interesting to see what are you actually getting more consistently, because you would no one really needs those peak rates in any practical use case, I would say. So it's really that you would like your service to work flawlessly wherever you are.
Right. So are we really sure about that, by the way? I mean, you said nobody needs these peak rates, but do we know that for a fact? I mean, you could think of future applications with virtual reality, augmented reality. You have all these machine learning algorithms that want to collect raw data from cameras and other sensors in real time. Do we really know for a fact that in 10 years that we won't be needing these peak rates? Or maybe
no,
that's
I'm exaggerating here, but I'm a firm believer that what you want to try to achieve in the future networks is not to deliver as high peak rate as possible, but to make sure that more people can get a decent rate. And that is also sort of what Massive MIMO is about, because it's not really about pulling up the data rate per user in a way, but to be able to serve multiple users at the same time. Because traditionally, these peak rates that have been mentioned, it's like you are one user in the cell, you are standing in the center of the cell, and you're alone, so you can get all the attention. But with the Massive MIMO product, the great thing is that multiple users can get equally high attention, and you sort of are not losing much in performance, even if you have multiple users in the same cell.
Right.
And in that way, sort of the peak rates might be roughly the same as in the past, but it's achieved in many more occasions.
Right. It's really this uniformity of the quality of service and coverage at the cell borders, cell edges that are the maybe most outstanding selling points of Massive MIMO technology.
Yeah, and you're not really having one cake of spectrum that you need to divide between the users, but as more users come in, the cake is growing, and everyone gets almost the same type of size of their slice as if they would be alone in a network. Of course, there is some interference, as you were mentioning, but up to a certain number, you are still benefiting. And that is also what is important in Massive MIMO. We say that we have, say, 64T, 64R, that we are having maybe only 8 users or 8 users with 2 layers each being served, because you have this difference between number of transceiver chains and the number of users, because user will typically not stand at ideal locations, so you need these extra transceiver chains in order to cancel interference and be able to see the difference between them.
So,
and this also, by the way, comes into when it comes to why some operators are buying 32 or even 16 products, even if the 64 is available. I mean, it's not necessarily only about the weight and the cost, but it's also because they think that at the place where we're going to deploy them, we won't see much benefits, because we're going to put it up in a place where, to say, you might have the same number as antenna element, as I was saying, but you have some that are vertically stacked and some that are horizontally. And with the horizontal, you can send beams in different horizontal directions. And with the vertical ones, you can send beams up and down. And then in reality, you send some kind of combination of many of those things. But if you are not believing that beams will come from different vertical directions, because you have a city where there's not much difference in the different elevation angles, or you are at the countryside, for example, where everyone have almost the same angle, well, then it might not pay off so much. You might not benefit much from having those additional transceiver chains that are giving you vertical resolution.
Right, I see. So that is the reason really for why, I mean, there are 16T, 16R variants of these products out there. At first sight, I mean, being an academic researcher in Massive MIMO, then seeing 16T, 16R feels a bit like sausage without meat. I mean, this is not Massive MIMO, right? But, perhaps it is, according to some definition, and I think I understand better now why there is even a market for products with that configuration.
Yeah, I think you can find deployment scenarios, real ones, where if you compare the 16 product with the 64 product, the difference in performance that you can deliver in the cell is very small, and that's why it doesn't pay off. That said, if you look in the curves in the academic works, you always see that the performance is growing with the number of antennas. And that is partially because what we are often assuming is that you are not having a panel for the antennas that is a sort of rectangular shape, but you have a long horizontal type of array. And in those cases, it pays that much more, because you get this high, as you add additional antennas, you are getting a better resolution in the horizontal domain. But if you are saying that, okay, if I add 16 more transceiver chains, what I will gain is just an improvement in how I can control my beam vertically, and not that by adding more antennas you can control it better horizontally. Well, then that is the reason.
Right, right. Yeah, so this is an intriguing issue, I think, with antenna array design and all these panels. I mean, to me, it's not at all clear why the antenna array has to look like a panel to start with, but maybe that's something we could return to at some other occasion. So Emil, I mean, given all this, where do you see Massive MIMO heading? What is going to be the next step in terms of products and in terms of commercial deployment? And where does the academic research stand currently? I mean, where are we heading, and where are we going to be in 10 years from now?
That is a large question to answer. I would say that there's different perspectives or different types of dimensions to that. One of them is sort of the thing that, okay, we have gone from having separate antennas, separate radios, now we're integrating the antenna radios in one box, and as we are able to squeeze down the size of the different components, it takes time to develop a system of a chip that are dedicated for particular type of things. But when we can shrink down the type of equipment that you can put or need to put into these Massive MIMO products, you can also control maybe all of the elements instead of just a subset of them, and the cost difference might not be so big anymore, and we might see base station array with a few more antennas, for example, in these bands, but then probably in the end it's the wind load and weight that will determine things. Then, as you were touching upon, I think one step is to have sort of multiple panels on the same site that are being connected to each other. Maybe you take many 16 T16R product and put them on the same rooftop, distributed from each other, and then you control those ones as some kind of distributed Massive MIMO system. And then we have all of the things around millimeter wave, the bands that are not being used so much in the first 5G deployments, but they will eventually be used. And there, the hardware evolution is still to happen. A lot of things are analog or partially analog. With time, we will see digital Massive MIMO product there as well. And as you go up in frequency, each antenna element becomes smaller. And that means you might even see products with 1,000 T's, 1,000 R, or you usually like to have a 2 to the power something, so maybe 1,024 times 1,024, for example.
Wow, that's amazing. I mean, a 1024 by 1024 array, right? So you speak of millimeter wave. I mean, we haven't really touched a lot upon millimeter wave here in the discussion, but you mentioned it now, and you also mentioned that, well, the hardware isn't as mature. Which band specifically are we referring to here? Is it like 60 gigahertz or 28 or 30 or something else?
So there are some operators that have been starting to deploy millimeter wave products, and then it's like 26, 28 gigahertz bands. For example, Verizon in the US are deploying things there for sort of outdoor coverage in cities along the streets, for example. And that, I think, seems to be the first bands to consider.
Right. Yeah. So I think I'm returning to this issue of array design, right? And when we speak of these panels, and then you might have like 64 or 100 or something, but then you said that where the wind load is like prohibiting, right? We can't make them larger because of the wind load, and I've always been thinking that this just can't be. I mean, this element should be naturally integrated into the environment or into buildings or other natural objects, perhaps. I believe that's a matter that we could also return to in more detail at a later occasion. So
yeah, definitely.
Yeah.
No, so I think traditionally, if you put up something on a mast, you're gonna have to pay the company who owns the mast based on how much wind load you are creating on the mast. So that's sort of today a business limiting factor.
Right. Yeah. Of course, there are. I mean, obviously, lots of limiting factors like that in practice, right? I mean, as academics, we tend to think only about the limits imposed by physics and by information theory, which I think is because those are really the foundational limits that are set by nature. Now, in a commercial reality, someone has to install all this equipment, someone has to pay for the sites and for all the cables and all these boxes and all the electricity and all that. I guess a distinction, though, is that, well, the laws of nature don't change, while the business reality might very well change and might change quickly. So I think this is again a question on, I mean, future deployments and future visions for what antenna arrays are going to look like. That's something that I think we should return to, Emil, in a future episode in more detail.
Yeah, they definitely, and it seems like really the hardware is now catching up with what people in academia have been believing for a long time. So when I did my PhD, I was thinking of an antenna as being the physical antenna, the radio, and the baseband processing just one thing, and I just considered a mathematical model for that. But then when you realize that, oh, for decades it has not been like that, but now we are taking step by step and actually integrating things together. We're putting a lot of things in one panel, and then we put some of the baseband processing in some cloud computer somewhere, and then we are very close to the type of deployments that people have had in mind in academia for a long time, but there's still a lot to do in the hardware design.
Right. Yeah. Well, okay, great. So, yeah, I think with that, we might be closing up here. Thanks a lot, Emil. That was a great discussion. Thanks to everyone who's been listening. And the ambition here is from Emil and myself to create a series of podcasts under the label Future Wireless or Wireless Future, and we'll be open to questions from the listeners. So if there is a topic that we could address and that someone is interested in, do send us a suggestion. You can reach us through email. If you search for us, if you watch the YouTube video, we'll put our emails there. Or if you search for us on the internet, I'm sure you'll find us. So with that, thanks again, Emil, and thanks everyone for listening, and bye-bye.
Thank you.